Thanks, everyone. Thanks for joining. My name is Jeffrey. I work for the OpenEBS project, and as was already mentioned, I was a little bit euphorical at this stage because I was working on something and finally worked. So I submitted this title to the call for papers at FOSDEM, and we'll see if we can actually achieve that. Hopefully, I can show to you a little bit later today. But to my defense, storage is not deterministic, right? Sometimes it has oddities there. So a little bit of a recap. So OpenEBS, last year I was here actually. I forgot to turn on the mic, so I hope this year is better. Touch briefly a little bit on how the SAN and NAS infrastructure came to be, and mostly to set the context around this concept that we came up with, and it's container attached storage, and what it actually is and what the purpose is. And today we'll talk a little bit more about the progress we've made in our maiden voyage with Rust, which was a very exciting journey. And we'll go over of the concepts that we've implemented, why we've implemented them, and why I personally believe that they make sense. As I mentioned, a quick demo. And if you hear something today that excites you and you would actually would like to join on the project, it's open source, obviously, but we're also hiring. So a little bit about OpenEBS. It's an open source project, started roughly 2 years ago. It's sponsored by my employee Maya Data, so I'm actually paid to work on this. And the idea is that we want to provide a cloud-native abstraction for cloud-native workloads, in particular for persistent volumes, right? So how do you do these persistent volumes in a system that's orchestrated in the cloud, in Kubernetes in particular? So as mentioned, it's built on Kubernetes, and one thing that Kubernetes has proven over time, I suppose, is that it provides, through the abstractions, it allows the developer to actually focus on deploying the application and not so much worry about the underlying infrastructure. So we inspired to do basically what Kubernetes does for apps, we try to do for storage in a meaningful way. So to give a little bit a vision about how we see this all happening. So imagine that you have several cloud vendors, could be on-prem, could be different type of vendors. You all run through Kubernetes, and what we want to build and what we want to provide is this declarative data plane that allows you to abstract away the differences between them, not just from a configuration aspect, but also from a data plane aspect, right? And we'll go over how we do that, because obviously that's non-trivial. So based on that, we capture a lot of information, and the idea is then based on the information we provide various technologies that give you some insight, visibility, advice in terms of how you should move your data and things like that, policies and what have you. So the motivation that this project has to begin with is, okay, so why are we doing that? And one of the things that we saw is that applications have changed and somebody forgot to tell storage. And what I mean with that is if you look at cloud-native applications these days, they have the scalability batteries and availability batteries included, right? So if you look at these new type applications, they are built with failure in mind, right? Across nodes, across DCs, across regions, and even cloud providers. Similarly for performance, they all kind of have this native scalability through HA proxy, Envoy, or what have you. So that leaves some room, let's say, for rethinking how you can do certain things in storage, because not everything is tied to this storage system, and then if the storage system goes out, everybody has a problem. The other aspect is that the people, very important aspect, the DevOps persona, right? They need to deliver fast and frequently. I just had a hilarious laugh last night because there was a very interesting video on Twitter about fast and frequently, but that's besides the point. The point here is that these applications are born into the cloud, so they adopt these cloud-native patterns, and now they want to move it back on-prem because they need to actually take it in production, and that's when the problems start to come, right? Because those abstractions that are true in the cloud are not necessarily true in their own environment. Another important aspect is hardware. Hardware trends enforce a change in the way that we do things. We'll go over those as well. But you can see these trends, propagate in all areas, right? So in the languages that we use, we have the concurrency primitives built in. And what I mean with that, in particular example, is Go, let's say, where you just go whatever, and you don't need to create pthreads or whatever. It's locked into the language. There are even languages that are even higher than that, cloud-native languages like Metaparticle, Ballerina, where you just, provide, basically describe the communication between these individual components, and there's that. So the hardware, And then obviously Kubernetes as a universal control plane to deploy these things. But the interesting thing is very recently, and this has fueled a lot of the work that I've been doing the last couple of months, is that if you're not going to the cloud will come for you. And what I mean with that is that you can actually, it's not publicly available yet, but things like GKE on-prem, where you get the GKE look and feel on-prem, and the same goes for Amazon Outpost. So people can actually buy point solutions from Google and Amazon to run these type of applications as they did in the cloud. And the other thing is that Kubernetes is starting to move towards also managing VMs, right? We can argue if that's a good thing. But the other side is that we see different type of VMs. There was a talk yesterday, Rust VMM, which is a perfect example where we basically strip down the hypervisor to the bare minimum just to get the isolation features such that we can run containers in production safely, because security is still not a very good solved problem in this space. So PVs and PVCs in a nutshell. There was a talk before this around CSI and all that, so you'll just go over this. But I basically sum it up as a PV is a mountable thing that you register to your cluster. Then you have a PVC, which you claim this mountable thing in your cluster, and you need to reference it in your application. And then there are some other things around that in terms of dynamic provisioning, so you do not have to register all these things manually, because that would be a tedious task. And that's a good thing, but it also has some implications, because your storage is like the mother of all snowflakes. It's very special, it's very purposely built, and they have all kinds of limitations in various dimensions that you need to consider when you're actually running Kubernetes on top of your storage system. But it is a lot better. And then you have the CSI interface, Container Storage Native Interface, that basically hides the vendor-specific implementation of actually mounting the volumes and propagating the mount points into your containers. So how does this look in YAML? So this is something that you probably should not do, because what I'm doing here is I'm mounting the local mount point of a node into the container spec. And as I mentioned, you really shouldn't do this unless you really know what you're doing, because the problem is when the workload moves away, your data is gone, right? And that seems like a no-brainer. Well, just don't delete the data. But the point is that your data needs to move with your application, right? So the canonical way of doing that then is through PVs and PVCs, and unfortunately, it's a little bit more YAML. And so we basically first create this persistent volume, and I don't go over the details here and what all these fields mean. That they're described on the documentation website of Kubernetes itself. And then you create the claim, right? So now I have a claim on this volume, and the final piece then is that I need to actually refer to that claim within my application. So that's a whole lot of YAML for a simple mount command, but it is what it is. It's the cost of abstraction, I suppose. But it does make sense if you run this at scale. And just for a single container, you're like, well, man, that's way too much. But at scale, it actually makes sense. So I think that a picture says more than 1,000 words. So imagine you have a two-node system. You have your PVC that is somewhere on a storage system. That's not important right now. And then you have your pod. And then you need to mount this thing. And this is what CSI helps for you. It does that automatically in the sense that it first connects it to the right host where your workload is. And it knows this because it works together with Kubernetes to figure that out. And then this final piece, let's say the blinking arrow, is the actual mount propagation, because it's containers, namespaces, so we actually need to do some additional work. And then the trick is, obviously, when the pod moves, then we need to do the same dance again. And there is an actual certain order in this, right? You cannot start the app before the PV is there. So it sounds trivial, but there's a little bit more to it than meets the eye in general. So the other thing is that I don't know if you saw it blink. It should have blinked, but the PVC becomes a very important thing here, right? Because as I mentioned, it doesn't work without it, for sure, but you also need to manage that data. How do you do that, right? So that's some of the things that we have looked into, and so is the problem solved with this PVC abstraction, and I can just plug in any storage system in there and be happy? But there are some more things to it than that, or at least we believe, and that is, how does a developer compose volume specific to its needs? So what I mean with that is that if you, for example, run MongoDB and you're using sharding, you don't need all these fancy features on your storage, and in fact, they might actually get in the way. if your storage system has a fixed endpoint where it replicates to, it basically nails you down to either that storage system or that storage system, and thus in the network and all these type of things. So you want some flexibility in certain cases, maybe not all. The other thing is, how do you unify the differences between the storage subsystems that you might have? So if you have DC1, you have a vendor A, DC2, you have vendor B. Okay, now I want to have a PV and I want to replicate this stuff. How do I actually do that? And these vendors go out of their way to make that, as incompatible as possible, right? So that's a thing that you need to consider as well. So what can we do to actually make that a little bit better? And the other thing is when you go into Amazon or GKE or whatever, and whatever you like it or not, what is kind of easy is you don't have to worry about anything, right? You just create a volume, it's there, you use it, you write it, and something crashes, and sure enough, there is your volume again. So this expectation in terms of how people use it, how they operate with it, that is something that we would like to bring to on-prem situations or cloud independent at least. So the gist of it is make your storage as agile as the applications that they serve. Now, there is a snake in the grass, for lack of a better word, and that is if you, as you create all these PVs on your storage systems, what you end up with, depending on your storage system, is this thing called data gravity. And whatever your storage system is, this happens by definition, right? And you can look up the term on the internet. There are a lot of articles talking about this. But everything evolves around your storage system, and the more data you store, the more application become dependent on that data. So it's like, this never-ending loop. So how can you break out of that data gravity aspect, and why would you actually want to do that? And one of the reasons is that all these storage systems, they have limits. They have limits in terms of latency, throughput, the I/O blender type like thing. And if it collapses, the whole universe is gone, or at least that solar system. So the other thing is the dimensions, as I mentioned already. Those volumes typically have a limit in terms of numbers, how many you can create. So a typical solution is, let's replicate the sun to another dimension. And, you could argue, okay, so that works, and it works great because we've been doing that for many, many years. But, it might actually make the problem worse. So when you talk to Picard about that, he's not really happy because he believes that, fighting the Borg, and the Borg is a reference to Kubernetes, which is the original paper, which I would suggest you read. So therefore, there's some Star Trek here. Anyway, so the OpenEBS approach, we thought about this. We all have a storage background, so we're not like new to this. But we didn't feel like, okay, let's build another distributed system that's even better than all the other distributed systems out there, right? So we really try to look into what is the problem that we're trying to solve. And one of the things is that instead of having these dynamic distributed algorithms dynamically figure out or calculate where the data should go, we actually allow data placement to be defined in YAML. And again, we can do this because Kubernetes is here, which has topology awareness and all these type of things. The other thing is we want to have it composable. Just like you compose your containers, we would like to be able for you to compose your volume and in turn on certain features or off that you don't need. And as you decompose those monolithic apps, certain things become possible because we're dealing with volumes that are 20 gig or 200 gig in size and not with petabytes of volumes that I need to replicate. So the inertia decreases a lot. Runs in containers, for containers, and therefore in user space. And the primary reason for this is that if you look at these different cloud vendors, they all have their own operating systems, right? And you cannot just load a kernel module in them because A, it's not available, and B, if you would do that, it would actually not support you when you have an issue. So doing this in user space seemed to be the most logical approach here, which requires a certain amount of tricks to make it perform, which we'll go over as well. So instead of having a big sun, we have a lot of stars, and Picard makes that thinks that's a lot better. So we try to do this. So to give you a little bit of so whatever, man, what does it mean, right? Okay, so data availability. So let's assume you're a developer and you're tasked with building an application, and you have 2 data centers, and your storage administrator says, you go figure it out because you're a smart engineer how to get the data there, right? That could be one of the things that you would need to do. So Like I mentioned, the replication between the vendors is not efficiently, or maybe it's not even possible at all. So you could, spin up your container and configure rsync and then say where it needs to go, and but that's all very static. It's not very dynamic, so that probably isn't a very good thing. So what we allow you to do is you can abstract away the differences between them, and we can insert ourselves within the data plane and do that for you, and you just specify what you want by declarative intent through YAML. And so how does this look? So you have your PV. Then you have your container attached storage system, and then you have the box 1, the box 2, the box 3, and this could be any box. This is actually a reference to the comedy show Silicon Valley. I don't know if you've seen it. It's quite entertaining. But we basically, as you put the I/O in there, we just fan it out through the 3 different subsystems. And what is important to note here is that the container, the CAS container, does the logging in and the actual replication, so it talks all these protocols to do the work for you. So you don't have to do all that work for yourself. The OpenEBS operator, which is not shown here, obviously plays a crucial role in making this all possible. It actually consumes the specific YAML components that you impose upon it when you create the PV and the PVC. So another example. So let's imagine that you have similar situation, but now you have different protocols. And these protocols can be the underlying protocols as well as the protocols at top. So what I mean with that is that you're running on host A, and it has a NVMe card with RDMA, and now it moves to host B, but it has no NVMe. So how do I switch dynamically between NVMe and iscsi, let's say, right? At the other end, and I'll explain this a little bit better later, at the other end, you have the same problem. So you might connect to a local device that's physically, locally in the machine, or an iscsi device, or a network block device, right? So abstracting away these differences is key here, or at least we think it's key. So to give an example again, so asymmetrical backends, that's where that comes from, because all these different protocols have different envelopes in the way that they perform. So you have this this problem then, let's say, where you want to get rid of this NBD device because it's slower than iscsi, and therefore it dictates performance depending on the replication model. So async, I think, speaks for itself. Semi-sync is basically where you say, okay, I want the 2 iscsi LUNs to acknowledge, and then the third replica, you can do that a little bit later between a certain amount of rules. And sync, I think that also speaks for itself. So imagine that you want to attach this new iscsi LUN, and then you basically want to rebuild or hydrate. They call it hydrate in the cloud native world. Probably sounds a little bit cooler than mirroring. And then once the hydration or mirroring is complete, it basically becomes a full replica of this whole set. And then you can just phase out the existing NBD volume, and there you go, you're on iscsi. And this is not just this is a little bit of a contrived example, obviously, but there are actual data migration paths that you need to do in data centers because your storage systems have a particular lifespan attached to them, right? They only operate for, let's say, 3 years. So you need to do this anyway, right? And it's always been a big problem in general to do. So a little bit about this rebuilding. So these, as I mentioned, those volumes are relatively small, right? So although small, you don't want to rebuild stuff that doesn't require rebuilding. So unused blocks, you don't want to rebuild. And the Ceph talk actually mentioned this as well, and that is you keep a bitmap, right? So these are not new things, man. This has been, people have been doing this for years, right? So I'm not going to pretend that I've invented the light here. I'm just reapplying what has been there. And the cool thing is that I actually have to do it on a far smaller size, right? So bitmaps keep track of dirty segments. The segments represent a region on the disk, and then you only copy the dirty segments off the disk to the other one. There is some things that you need to do because while you're rebuilding, another dirty segment gets created. But again, these things this is not rocket science. We've been doing that for many years. So small. So if you look at if you look up Google Bonwick space maps, you'll see what I mean with small, because the space maps are a way that ZFS, which you probably have heard of it, can do petabytes, because if you have a bitmap for petabytes, the bitmap is huge, right? So, but in our case, the bitmap is small, right? So that's very key. Thin provisioning, snapshot clones, obviously you want to have that. I won't be talking about that now, maybe next year. But as I mentioned, this is nothing new. It's not all that interesting. So composable storage. Okay, what does that mean, right? Sounds cool, but what can I do with it? So you have these, again, in Kubernetes, they don't really talk about input-output. They talk about ingress, egress. Okay, so whatever. We'll use that. And then you have so you have your input, and then you have your output, which points to a device, whatever it is. We'll get to what type of devices later. But then you can add these translation layers in between based on what you need, like, for example, compression, encryption, and mirroring in this particular case, right? And the order is important here, so don't encrypt and then compress, but yeah. So in order to build this stuff, as I mentioned, we needed a language that actually allows us to accelerate a little bit. So we opted for Rust, which was an interesting journey. The thing there, the unsafe, actually disables optimization for the compiler. It doesn't have certain constructor attributes that you would be used to in C, so it's a little bit of a sidestep here, but it was quite interesting. So let's look a little bit into mirror device, very high level. I actually had to remove a lot of code, and you can't actually see the comments, which is unfortunate. But basically, this is a structure of a mirror device. Based on the YAML, we actually enumerate over the YAML, let's say, and then we open all those sub-devices for you, and then every I/O goes through the childs, which you can see. Again, I removed a lot of stuff here. So at the very end here, we match it the I/O type. If it's a read, we'll do the read. If it's a write, we'll do the write. But the most important thing is here, this is for OBD, that stands for online block devices. We basically iterate over all of them. And the policy that we apply here, that's what we determine before we actually go to the I/O. If there's an error, then we basically said that there was an error on the I/O. And then in the completion handler, again, based on the policy, we'll figure out if the I/O failure is critical or not, or will you just say, okay, I had 3 of the replicas replied, my policy says 2 is enough, so I'll just continue. So declarative, what does that mean in YAML? Kind of looks like this. So you basically define what type of volumes you want, where they are, if you need to, because we can actually do the TIM provisioning on bigger volumes, so when you set this up once, that's no problem either. The properties that you want, so you can actually compose your storage the way that you want it. So a little bit more about these protocols, right? So I have my PV, and then I have my container. Normally, you talk to a storage system. Okay, so how do I connect, right? This was really key, because one of the things that we don't want to do is impose a cost that is unacceptable in terms of performance, right? Because, you know, at the end of the day, it's all nice, but if it doesn't perform, you know, it doesn't really work. So what we do here is we basically have a set of protocols that we support. The VirtIO family is very important, again, for these new type-like hypervisors that, you know, are the stripped-down ones. They typically use VirtIO to do I/O very efficiently, because those kernels know how to work with virtualized I/O. And then we have basically the input path, and then there is the output path, which can be, well, I won't say everything, but a lot, right? So Gluster is one of them. We can just write to that, or another iscsi, or a local block device, which we access through AIO, and so forth. So, and then when you construct a volume with this YAML, it basically just fans out and, you know, could do a transformation or not, right? Okay, so let's talk a little bit about this performance aspect of it, because performance, particularly doing I/O in user space, there are some challenges to that. And what can we do to mitigate that? And so one of the things is, when you look at CPUs these days, they have these MMUs in the I/O MMUs, and these are very important in terms of the misses that you can get and the impact they have on performance. So a solution to that is to use Hugepages. And they're not actually all that huge. They're only 2 megs. But I don't know if you can see it. But the 4K pages, we have 22 million misses. And in the lower end, we have 0 misses, right? So, and this is really beneficiary for performance. The other thing is that once we start up, the allocation is static, right? We don't need more capacity or memory as we plow through performance, because we just pass the performance on, unless you do compression, but we basically allocate these things up front. So Lord of the Rings, one of the things that, as I mentioned, the hardware has changed, and so what can we learn from these hardware changes, and how do we make sure that we use them optimally in the software stack? So it's kind of interesting to see with the lines that I tried to put on top of that, is that the number of logical cores has been increasing, and the frequency in hertz basically stagnated back in 2000, is at a dead stop. So more cores, and that means that if you want to utilize these cores, you need to change your software approach to that. And this is exactly also what the NVMe spec does, is that they use all these type of rings, and each ring refers to a particular device, and each core has its own ring, so each core can talk to any NVMe device without any locks in between and whatsoever. And there is some other interesting things. So this is Jens. He's you guys probably know him as the Linux kernel block maintainer. He's the author of the block MQ layer. So a very smart guy, and he's actually been implementing this ring approach in the AIO subsystem. And I've highlighted the word ring, and this is just one of his bullets, actually. And so you can really see this pattern of submission queues and completion queues and rings come back in the whole I/O stack. And the reason that he's working on this in particular is he wants to mitigate the Spectre and Meltdown patches. So with this code, when you do I/O, you don't even go to kernel space at all, right? So you write it in a ring buffer, and the kernel does the submission for you, and you just pull for completion, right? So we use the same thing in container attached storage. We're leveraging code from SPDK there. So there is this puller, which basically, so we have an iscsi socket, right? So we're listening for iscsi, and we're constantly reading on the socket with the read call, and basically we're doing this non-blocking. So we do the read, and say E would block, and we just continue to the next thing, and just keep spinning like a madman in order to see if there's work. If there is work, however, we get this, whatever the job is, let's say read or write or an inquiry command, whatever, there is a message placed into this ring, which then gets read by the reactor. And this is typically a function argument 1, argument 2, but this is abstracted away in terms of I/O channels. So you don't actually have to send the message, but you work with I/O channels, so to make it a little bit easier. And then there's also a management interface, obviously, because it pulls the same way. And then there's actually the devices that you need to pull as well, in terms of, okay, hey, there's an interrupt, or I'm ready, or whatever. So efficiency. So people ask, hey, but you're pulling constantly. What does that do for performance? So this is the same machine. At the top level here, you can actually see that the CPU idle is the right column. So the more idle, the better, right? And you can see that the load is actually divided between kernel space and user space, as you would suspect with running this thing the traditional way. And the thing here below is where we run completely in user space, right? And the thing that you don't see normally is that what the kernel in the background does when you actually do the I/O. So you would think, hey, this is not efficient, but it turns out, and the numbers speak for themselves, although very small, but nonetheless, right? We have a very low, or we actually are more efficient, right? But that's just not the goal to show here. The goal here is that pulling is not a problem. And in fact, kernels actually in the background dynamically start pulling anyway, right? You just don't know about it. So this gentleman, Avi, who is the author of KVM, he's working on a database. They use similar constructs from DPDK in their software, and he sums it up pretty nicely. If there's no load, yeah, we're probably a little bit more inefficient, but if there's high load, we are far more efficient. So the same holds true here as well. So nvme-tcp has been ratified somewhere in November, so I was trying to make that work. Didn't go very well, as you could see, but I figured it out eventually. And the point here is that protocols matter. So I have this micro 1.9 terabyte NVMe SSD, who on spec can do 840K IOPS. So this is just a huge amount of IOPS, right? I mean, come on, it's just insane. But anyway, so we run the software using UIO. So we basically map the PCI registers into user space, and we write directly into user space into these registers, and we get close to 960,000 IOPS a second. It's very likely this performance will degrade over time, because that's the nature of SSDs, but it will probably steady state around this 840 spec. Then I did the same thing, export that device through a network block device protocol, and it could only do 100,000 IOPS. And the problem here is that the syscall rate dominates performance here, and that's due to the fact that how NBD is designed, right? Each IO is a syscall. iscsi does a better job. You can log in multiple times, and then you get close to 500,000 IOPS, but that's where it basically starts to become a problem as well. So the solution to that obviously then is iscsi over TCP, or iscsi, not use iscsi, but use NVMe over TCP. RDMA goes a lot faster, but through RDMA, you actually need special hardware, you need special switches, and that's probably a big tax on your infrastructure. So how can you leverage NVMe in your existing infra without throwing away all your hardware? And NVMe-tcp is the solution for that. It's not rock solid stable, so this is only available in the RC kernels 5.0. But I did a very, I wouldn't say scientific test, but nonetheless, I did a test on my laptop, and just by same device, same setup, same laptop, same VM, or whatever, just switching protocol just gave me a 30% increase. And the reason for that is not because NVMe-tcp is so much smarter in the sense, but the reason for that is that the things that it does not have to do, right? So less is more, and you get that through performance. Because this whole block layer request, the SCSI layer, the HBA, and all these types of things, that's completely gone in the NVMe space, and therefore it allows you to do some better performance. So I want to show you guys real quick how that, I hope at least I can show it real quick. Yeah, okay, so, okay, this, I have to, okay, anyway. So I have this tool here that, if I can type. So I have this tool here. I have these egress things, right? So I'm skipping all of that, and I'm immediately writing into the underlying layer. And the reason that I do that is that I want to measure the incurred performance when you, for example, add encryption, or when you add encryption with compression. What does that do for performance? Because you need to figure out, how these things behave. So, to give you a little bit of an example on what's the file name? So yeah, so the configuration file here. Oh shoot! Let me see if I can. Oh, darn it! Okay, that's unfortunate. You can't see that, right? Ah. Okay, so, wait, maybe. I should have known better not to do demos. Okay, so this is a Pandora device. It's a null device. So basically what it does is it grabs the IO, throws it on the floor. Okay, what good does that do? Well, actually, the kernel has a thing similar called null block, right? And it's a common thing to do, right? How do you measure overhead in the block stack? By having a block device that's infinitely fast, right? How do you do that? Don't do the I/O. So it's a little bit of cheating. So let me actually move my terminal back to my laptop so I can actually see what I'm doing for a sec. It's actually, I'm going to, I'll show you what I've done because I want to set it up real quick so that you can see that it composes several devices out of multiple. Typing under pressure is never good. Okay, there we are. So what I've done is, yeah, so I hope it won't mind that thing's still there. So I'm going to create 3 of these devices, and then I'm going to, add this layer of mirroring where I grab these 3 devices and then do I/O to it, right? Not all that interesting, but the thing here is, so how fast is it, right? Because if this is slow, I'll never go fast. Where's my mouse? Oh, I'm never going to do this again. Okay, so I'm going to start the thing. I have to give it the configuration file, and I'm going to give it a queue depth of 1 because that's what devices don't like because it shows how slow they are. And I need to specify a block size, so we'll do this. A time as well, because otherwise it will just run forever. And I think that's, oh yeah, what we want to do some random writes. Whoa. And so you see some of the Hugepages. It constructs the mirror device based on this thing. And that's a little bit over 3.5 million. So 3 devices we're mirroring, and we have, we're doing 3.5 million. So we actually broke that barrier. And just to show you that there is obviously one last thing, and then I'll be done. Never mind. Just questions? Yes. Yes, sir. No, I have not. That's oh, sorry. So you're So I did not turn on multi-con support for NBD. That is very true. That is very true. And my point was not to find the absolute numbers of iscsi versus NBD. What I wanted to show was that there is a difference between the protocol that you select, what the performance envelope is. Yeah. Any other questions? Okay. Well, thank you very much, and until next time. Thank you.